So let's take a look at some of those conceptual questions. Alright, so number one, this is a true or false question. A tile falls from the roof of a building to the ground. Its momentum is conserved. True or false? It would be false. That's true. Why, though? Why is the momentum not conserved? Say that again?
It's falling faster.
It's falling faster and faster every second. Yeah, but what was the condition under which momentum of the system was conserved? Something had to be true. It's not always true, but something has to be true. Correct. The net external force acting on that system, the unbalanced external force acting on the system, should be zero. For example, this ring. Right now, what is its external force? The net external force acting on that ring?
Zero.
Zero. Therefore, it will preserve its momentum. It has zero momentum now, and it will continue to be zero through time, because there's no net external force acting. This tile, not so. There is a net external force acting on it. It's mg. Therefore, that block will not, or that tile will not conserve its momentum. It's going to fall faster and faster and faster and faster every second. So it's gaining negative momentum, okay? Because there's an external force acting. So the answer to this one is B, false. The reason is because there is an external force acting. Okay. So take a look at number two, conceptual. Number two, conceptual says the following. A stock person at a local grocery store has a job consisting of the following 5 segments. Number 1, picking up a box of tomatoes from the stockroom floor. 2, accelerating to a comfortable speed. 3, carrying the box of tomatoes at a constant speed. 4, decelerating to a stop. And 5, lowering the box slowly to the floor. Okay. And it wants to know in which one of those processes did you do positive work. Okay. So let's do the first one. So pretend that this is the box of tomatoes. How much potential energy does that box of tomatoes have right now? 0. So in order to elevate it to some altitude, does everybody agree that I would have to increase its potential energy? By the very fact that I'm increasing one form of its energy, namely its potential energy, I have to do positive work on it because I am increasing its potential energy. So by just doing this, I have done positive work. Now, if you want to think about it in terms of the cosine and all that stuff, I have to apply a force that is up, would you agree? And I'm also moving up. So what's the angle between the displacement and the force?
0.
0, and cosine of 0 is a positive 1. So I'm doing positive work. Now, you can think of it also as you're increasing this body's potential energy. By the very fact that you're increasing its energy, you're doing positive work. Okay, so number 1 is definitely positive. Number 2, let's take a look. You're accelerating it to a comfortable speed. So right now, how much kinetic energy does it have? 0. But now I have to accelerate, because if I want to get this guy from here to here, from here to over there, right? I have to first speed it up, right? I have to move, right? So I have to now accelerate. What have I done to the kinetic energy by accelerating up to a comfortable speed? I started with 0, and then what happened? I have increased its kinetic energy. Does everybody agree? By the very fact that I increased one of its energies, or one of the forms of its energies, what have I done? Positive work or negative work?
Positive.
Positive work. So 1 and 2 so far, positive work. Now, once I've accelerated up to a comfortable speed, now I'm going to travel at constant speed. So this is now constant speed. Am I changing the altitude of this object? So therefore I'm not changing its potential energy. What about its speed? Am I changing its speed if I'm traveling at a constant speed? No, so I'm not changing its kinetic energy either. Therefore, I'm not changing any of the energies. Does everybody see that? Therefore, I'm doing 0 work. Does everybody see that? Now, so 3 is 0 work. I'm not doing any work. 4, decelerating. So now I have to put it up on display, right? So I have to slow it down. Have I decreased its kinetic energy or increased it?
Decreased.
Decreased it. By the very fact that I've decreased one of its forms of energy, I've done negative work. I had to take away all that kinetic energy that it had, so I had to withdraw that energy. So I did negative work. Yeah?
I have a question about number 3 real quick. If the force is going in the same direction as...
We're going to get to that, yeah, in just a second. So take a look at, so decreasing, so that's negative kinetic energy. So take a look at number 5. So it says lowering the box slowly to the floor. So here I have positive potential energy, right? Now, so I have potential energy. Now I'm going to lower it. Am I decreasing its potential energy or am I increasing its potential energy?
Decreasing.
I'm decreasing. So therefore I'm doing positive work or negative work?
Negative.
Negative work, excellent. But since it asked for in which case do I do positive work, does everybody agree that only 1 and 2 will give me positive work? Does everybody agree? So that answer to that one is going to be D. Okay, that's the only time I do positive work. All right, so take a look at number 3. So number 3, it says, if a force always acts perpendicular to an object's direction of motion, that force cannot change the object's kinetic energy. So let's take a look. So let's say, for example, I give you something like this. So let's say there's a table, and there's a rope, and there's an object that the rope attaches to an object, and the object is being swung around in a horizontal circle. So, question for you: is there tension in that rope?
Yes.
Yes. If I look at it from above, this would be a top view. So take a look at this. If I look at a top view, does everybody agree that it would look something like this? I would have the rope, and here's the mass. Does everybody agree that it would be going around in a circle like this? That would be like a top view. Does everybody agree? So now, would you agree with me that at this moment in time, let's say that it's going counterclockwise. Watch my pen when I get here. In what direction am I moving in at that moment in time? Does everybody agree that it's in this direction? Tangent to that trajectory. What about at this moment? Again, tangent to the trajectory. At this moment, tangent to the trajectory. So I'm going to draw it for various locations. That would be the velocity at various locations, right? But if you notice, since the tension is always pointing towards the center, it's a centripetal force, does everybody agree that the tension is always perpendicular to the velocity? Would everybody agree with that statement?
Yes.
So therefore, the tension is always perpendicular to the motion. Does everybody see it? It's always at right angles with the motion because it's always perpendicular to the velocity. So when the force is perpendicular to the motion, if you remember for a constant force, you had this situation, Fd cosine of theta. Does everybody remember? What would be the angle in that case between the motion, the direction of motion, and the force? What would be the angle? It would be 90 degrees. Very good. And cosine of 90 is 0. So this force, since it's perpendicular to the motion, does absolutely no work. Okay. Would everybody agree that this force does no work? Now, that wasn't the question, though. The question was, when a force is perpendicular to the motion, it cannot change the body's kinetic energy. So, but everybody agrees why the work is 0. Does everybody agree? So let's say, for example, this were the only force acting on this object. A force that is perpendicular to the motion. Would you agree with me that we have an equation that relates the net work on a body, or the net energy transfer with a body, or a system, and the change in kinetic energy of the system, or body? Does everybody remember? That's called the work energy theorem. So let's say that that force that is perpendicular to the motion of the object is the only force acting. Would you agree with me that the net work would be 0? Because the work that that force did was 0. Does everybody agree? So therefore, 0 is equal to the change in kinetic energy. Does everybody agree that that would predict that the change in kinetic energy of that body or system is 0? By the very fact that the force was perpendicular to the motion. Does everybody see that? So that's a very important concept. All right, so that's going to be true. If a force is perpendicular to the motion, it cannot change the kinetic energy. All right, so take a look at number 4. So number 4, this one talks about 3 cars. So this is number 4. So it says we've got 3 cars, F, G, and H, are moving with the same velocity, and the driver suddenly slams on the brakes, locking the wheels. The most massive car is car F, the least massive is H, and all 3 cars have identical tires. Okay, which one is going to have the highest stopping distance? That's the question. So, for stopping distance, what I'm going to do, let's say that I have a car of mass M, okay, and it's traveling with a velocity v naught. And I want to figure out, this person slams the brakes and locks the wheels. What's going to happen to that car? It's going to start sliding. Does everybody agree? And we want to know how far that car slides before it finally comes to rest. V final is 0. So this is going to be some kinematics. We can do this with kinematics. Shouldn't be a big deal. So stopping distance, remember from chapter 2, we used this equation. Does everybody remember? This was the equation we used. What's the V final?
0.
0 equals V initial. We don't know. We're going to write it completely generally in terms of V naught, right? So V naught plus 2 times the acceleration times the delta x, which I'm going to call d. That's going to be my stopping distance. Can I now solve for that stopping distance in terms of the initial speed of the car and the acceleration of the car? Does everybody agree? So I can go ahead and do that. And when I do that, I end up with the stopping distance being equal to negative V naught squared over 2a. Now it looks strange. It looks strange because it almost looks like the stopping distance is negative. But that's not the case. Look at this. Does everybody agree that that is a positive number? Yeah. V naught squared is a positive number, right? And what does V naught stand for again? The initial speed of the car. Okay, so we're writing the stopping distance completely generally in terms of the initial speed of the car and what the acceleration is. Okay, 2 is a positive number, so far this is positive. Does everybody agree? So far with this extra negative sign, the stopping distance would be negative, right? But look at the acceleration. Does everybody agree acceleration is a vector, so it has direction? So if we're traveling to the right, in order for this car to decelerate, does everybody agree that its acceleration would have to be opposite the motion? So actually the acceleration is negative. And that negative would cancel out, so it's like a deceleration. That negative would cancel out this negative, so I could actually explicitly write that by putting the magnitude of A and getting rid of this negative sign. Does everybody see how I got this? Now here's the question. Is that distance dependent on the mass of the object? Does everybody agree that it does not depend on the mass? So the answer to the first question in that problem is they all travel the same stopping distance. Okay. So that's going to be D. This is completely independent of the mass. And remember, it said that the tires were the same. So the second part of this question, this was for part A of the question. The second part of this question, part B, says, for which car does friction do the largest amount of work? Now, when friction is doing work, does everybody agree that that means that friction is dissipating the energy? Does everybody agree? We have to dissipate energy, right? Because a car that is moving, does it possess any energy right now? What is its potential energy right now? It's on the ground, right? What is its potential energy?
0.
0. Does everybody agree? But it's moving, so does it have kinetic?
Yes.
Yes, it does. So would you agree with me that friction would have to do negative work to withdraw all of that energy? And what is friction going to do? It's going to turn it into a different form of energy, which is heat, right? Thermal energy. So let's take a look. I'm going to have the smallest car, the medium car, and the largest car. And then I'm going to ask you a question. They're all three of them are traveling at the same initial speed. Which one has more kinetic energy to dissipate?
The biggest one.
The biggest one has the most kinetic energy to dissipate. Does everybody agree?
Yeah.
So would you agree with me that in this case, the heaviest case, friction would have to dissipate the most amount of energy? Would everybody agree? So therefore, in this case, work done by friction would be the highest. Why? Because this guy possesses the most amount of energy out of all three of these. So therefore, friction would have to dissipate all of that energy into heat. So in this case, it would be the most amount of heat generated. So the answer to the second part of the question is car F, which is the heaviest car. This is car F. So the answer to it is A, car F. All right, so take a look. So in which case do you expect the tires and the brakes to get the hottest? In the heavier case or the lighter case?
The heavier.
The heavier case. Does everybody see that? Okay. All right, so take a look at problem number 5, conceptual problem number 5. It says,
Before you go on,
yes.
I don't have the paper in front of me, so when you got the answer to part A for 4, what are we looking at there?
This is stopping distance. So which one has a larger stopping distance? If they all have the same tires and brakes and all that. So that's going to be same, because it doesn't depend on mass. Yeah. All right, so take a look at number 5. So number 5 says, consider 2 less than desirable situations. In the first, you're driving at 30 miles an hour, and your car has a mass m, and you crash head-on with an identical car. What does that mean, identical car? That means that the mass is the same. So an identical car of mass m, traveling in the opposite direction, therefore negative 30 miles an hour. And in the second option, you have a car that has a mass of m, traveling at 30 miles per hour, but this time you hit a wall. Okay? In neither case does your car bounce off the thing that it hits, and the collision time in both cases, which I'm going to call delta t, that's the amount of time it takes for me to lose or gain momentum during this process, during this momentum transfer process. Delta t is the same in both cases. So the question is, which one of these two situations would result in a greater impact force? So that's the question. So in order to answer that, first I have to ask you, in this system, how much momentum do I have in that system right now? So I'll call that P initial system. How much momentum do I have?
0.
0. Does everybody agree that I have 0 momentum here? Momentum's a vector, right? So it can be canceled. So this would be m, and I'm not going to write the conversion here. Just remember that 30 miles per hour, this needs to be converted. But in this case, really it doesn't matter because it cancels anyways. So plus mass times negative 30 miles per hour. What do you end up getting? Does everybody agree 0 Newton seconds? Again, in reality, this would need to be converted. But since they're the same and negative of each other, they end up giving you 0. But if it doesn't happen, you need to convert that 30 miles an hour to meters per second. Okay. So I have 0 Newton seconds. So when these two cars crash, and I believe I did a demo like this in class, they crash, they stick together, what happens to them? Stop. They stop. Does everybody agree that they're going to stop? So that means, say this car right here. Would you agree with me that it started off just the car by itself, not the system? We know that the system has 0 Newton seconds of momentum, right? Do you agree with me that this car right here starts off with a momentum of m times 30 miles per hour? Would you agree? Yes. And when it finally hits this car, they stick together and they stop. How did we know they would stop? Because the final momentum must be the same as the initial momentum. Momentum's conserved, right? So when they finally hit each other and stop, tell me, what should be the final momentum of that car? This car, not the system anymore. This car, how much momentum should it have? It's going to stop. It should be 0. So would you agree with me, and I'll just write units, would you agree with me that I have lost some momentum? How much momentum did I lose? mv. Does everybody agree? M times 30. So momentum lost, which I'll call delta p. That's the impulse, by the way. That is the amount of momentum that this car lost when collided with this car. That is going to be equal to mass times 30 miles per hour. And it's negative. Why? Because I could do P final minus P initial. Does everybody agree that I could do P final minus P initial? Here I'm not adding. Here I'm just finding out the difference in momentum during this process, right? For this object. It lost momentum. So it's going to be P final, which is 0, minus P initial, which is m times 30 miles per hour. So does everybody agree that I've lost this much momentum? Mass times 30 miles per hour. Of course, 30 miles per hour needs to be converted into meters per second, but I'm just going to leave it like this because that's not important. Now in this case, how much momentum do I start with before I collide with the wall? Mass times 30 miles per hour. Does everybody agree? And what about P final when I finally hit the wall and come to rest? That's going to be 0. But wait a second. Isn't that exactly the same that's going to happen here? Does everybody agree? So that means that my delta P, my impulse in this case, I still lost m times 30 miles per hour of momentum. Does everybody agree that the impulse is the same in both cases? The amount of momentum lost in both cases is exactly the same. Would you agree with that statement? Yeah. So therefore, if you remember something that I discussed at the beginning of chapter 9, the force, the average force, F bar, would be delta P divided by delta T. Does everybody agree with that statement? So the delta P in both situations is the same. And the delta T, it told you in the problem that it was also the same. So what would happen to the impact force? Does everybody agree that the impact forces in both cases would be exactly the same? So the answer to this one is the force is the same in both cases. So that would be C. Okay, so does everybody see how we got that? Does everybody see that? Okay, so take a look at number 6. So number 6 says a solid sphere, solid cylinder, and a solid pipe all have equal masses and radii. And it says are of uniform density. So it says if the three are released simultaneously at the top of an inclined plane and roll without slipping, which one will reach the ground first? So which one's going to reach the ground first out of all three of those? It's going to be the one with the least inertia. Okay? Least inertia means it's the easiest one to what? To rotate. So the one with the least inertia is going to be the solid sphere. Okay? So that's going to be A. And the way you can tell that is for the sphere, it's 2/5 mr squared. So that's for the sphere. For the disk, it's 1/2 mr squared. For the other guy, which is the, what's the other guy? The hollow pipe. So the hollow pipe is mr squared. So do you agree with me that if it told you in the problem that the mass and the radius is exactly the same in all cases? Does everybody agree? So the only thing that will then dictate which one of these inertias is larger will be the coefficient. Does everybody agree? In this case, the coefficient is 1. In this case, it's 1/2. And in this case, it's 2/5. Does everybody agree? Because it says that the masses and the radii are the same. Out of all of these, which one is the smallest fraction? 2/5 is the smallest fraction. So the sphere has the least amount of inertia, so the least amount of resistance to acceleration, to angular acceleration. So therefore, the sphere will reach the bottom first out of all of them. Okay, so that's going to be A. It's going to be the sphere. All right, so take a look at number 7. Yes?
You said for anything involving inertia, you would provide us
Yes,
those?
these I will give you, yeah. So you don't have to memorize this. Yeah. So in a problem that involves this, I will give you what the inertias are.
Okay.
Yeah. I may also put them on the board.
But
so
if you
have them.
hadn't provided that, what would you use to make that decision?
You have to actually know that.
Okay.
Yeah. So in order to solve the problem, you need to know that.
Okay.
Yeah. So there's no way to do it without the inertias. You have to know. I mean, unless you remember, that the sphere has the least inertia out of all three of these. But otherwise, to prove it, you would have to actually show the equations there. Yeah.
Is part of that because the sphere has the least amount of contact with the surface?
Not really. The reason for it is because the sphere has its mass distribution has it so that there's less mass further away from the axis of rotation. Remember that inertia has to do with how far the mass is spread out away from the axis of rotation. Remember, the further away that mass is from the axis of rotation, the harder it is to spin it. The harder it is for a torque to give that object an angular acceleration.
Okay.
Yeah, so it has to do with mass distribution away from the center of rotation, basically.